We're back with the stunning conclusion to the photoelectric effect. Okay, so last time we were here, we talked about the wave theorists and the particle theorists, how they had different ideas. The particle theorists were all about like Max Planck and the crazy ideas of energy being quantized. The wave theorists were like, if you make the light brighter, more stuff's gonna happen. Duh. And the intensity or the frequency does nothing there. So let's take a look at this. This is a simulation found on PhET of the photoelectric effect. And what we have here is the following. We have a battery or an EMF, and this EMF is connected to what is referred to as a salt plate. Now, these salt plates, and we call them salt plates because the one is sodium, it is a gap here, but if we're able to release electrons from the salt plate by shining a light on it, these are the photons from our light up here coming down, striking our salt plate. If we release the electrons, these electrons can flow, and then we can measure a current, because that's all electrons moving are, right? So let's do the following here. Let's see, just experimentally, what happens when we mess with some intensities and when we mess with some frequencies, what's going to happen. So both sides argue that when we increase the intensity, we should get more electrons coming out of this salt plate, okay? Oh, look at that. Now, the wave theorists argue that when I increase this intensity, I should get higher energy particles as well. Should get faster kinetic energies. The wave theorists believe that. The particle theorists believe that there is some maximum kinetic energy here. So if I crank this, we see that we've gotten more. Some are moving fast, some are moving slow. Well, that kind of helps the particle theorists because, like, that work at maximum could be an idea. Or we could have some other amount of kinetic energies, right? Here, you know, all those kinetic energies should have gone up, and they're not all moving fast. So the wave theorists are already in a pinch. Let's change the frequency and see what happens there. Right now, I'm at like a violet-purple light, 400 nanometers. I'm going to increase the wavelength. When I increase the wavelength, I decrease the frequency. So I'm going to move this to the right. And notice when I get to green, I'm still ejecting electrons here. But notice they're moving a lot slower. Given by this equation here, when we changed this frequency, we increased the wavelength, we made the frequency smaller, we're getting less maximum kinetic energy here, which means that these particles aren't moving as fast. In fact, if we get to a specific point, we just might not eject any particles. We could have gotten past that cutoff point, that cutoff frequency, and we're never going to eject anything, even if our intensity is maximum. Bunch of stuff? Nothing. So that is what we see with the photoelectric effect. We see that the particle theorists, using this equation, kinetic energy max equals hv minus the work function w, or phi if you want to use that, this is correct. This is what Einstein won his Nobel Prize for. Whenever Einstein came up with relativity, people really didn't think relativity was a thing. They were like, yeah, that's a bunch of hocus pocus. That doesn't make any sense. We don't understand this. We're not giving you a Nobel Prize for that. He got one for the photoelectric effect, which in and of itself is phenomenal. It wasn't until years later that they were actually starting to be able to prove some of the ideas of specific and general relativity. Even today, we're still running experiments to continue to prove Einstein's idea of relativity is correct. So this is the photoelectric effect here, just like that. Now, one thing that is fascinating to look at here is this graph. And it's kind of hard to see, so we'll actually blow this graph up a little bit larger. What this graph is showing here is the following. And this is a very important graph. This graph here is showing the kinetic energy and the wavelength. Or, excuse me, not the wavelength, the frequency. Potato, potato. And if we look at this right here, we notice we get a nice straight line that actually hits the x-axis. So we'll draw a line like this. This graph right here is very powerful. Graphing is a huge thing in the sciences, and with a simple graph like this, we can actually get a lot of information out of it. For instance, this point right here, this is the minimal frequency needed. It's the cutoff. It's the threshold frequency. In reality, the kinetic energy is going to be 0 up until that point, and then it's going to start going up. But since we were able to backtrack this line here, we notice it intersects the y-axis. This point on intersection of the y-axis, this is the work function. This is how much work that you need to do to remove an electron. And the slope of this graph has a specific value. It has a specific value that you might not have been expecting. Its specific value is Planck's constant. Once again, a constant that Max Planck thought was just gibbledygook due to mathematics just popped up again on a completely different experiment. If you were to change the different type of salt plate from sodium to zinc to copper to platinum to whatever you're using, this graph will be nearly identical, but your work function will change. That work function will shift. You'll have a new work function. You'll have a new threshold or cutoff frequency, but your slope will still remain Planck's constant. Because all this graph is showing us here is kinetic energy equals h nu minus work. This graph is literally just saying y equals m x plus b, where our b is a negative quantity. Your standard slope, standard graph, what you learned in your algebra and geometry courses ages ago, is what Einstein used to win a Nobel Prize. But those particle theorists had to take a leap of faith in believing Max Planck was correct. This graph is critically important. You must understand how to read it and what is going on. Okay? Remember, this y-intercept down here, this is your work function. Where you cross the x-axis, those are your threshold frequencies, or your cutoff frequencies. The slope will be Planck's constant, and if you're below that threshold frequency, technically, you have 0 kinetic energy. You are flat on the x-axis. It's only by backtracking this line that you can see what that work is. So that's our conclusion to the stunning photoelectric effect and who won that, wave or particle theorist. It was the particle theorist with Einstein. This was the graph that they used to do that, and this little simulation is a great way to see what's going on there. that the intensity just brings you more items, but it is the frequency or the wavelength giving us that frequency, as we see in here, that really shows us these changes of kinetic energies as we start getting into X-rays here, very high energy particle or photons coming in. These particles zip, and we go into infrared, very low energy. We don't even have everything. We've gotten below our cutoff. Okay? So that's what's going on there. Nothing too crazy. For now, this is finished. In a later video, we'll take a look at some examples of working out mathematically some photoelectric effect ideas, and then we're starting to get into some relativity concepts briefly later on. But until then, adios, and take it easy.